been here for over a decade. I'm a sales representative, and today we're going to cover modern boiler room concepts. A little bit about Wallace Innes before we start. We're a manufacturer's rep agency representing some of the finest manufacturers of HVAC and plumbing equipment in the United States and from all across the world. About what we are we provide design services, we provide equipment selection, and we have an excellent service department. We've been around for over 95 years. And one of the other things that we do now is we also do skid packages for pumps and boilers as well. We're a full service agency, and our manufacturing partners, as you can see, are some of the best in the industry, including Bell & Gossett, Lochinvar boilers, and as you can see, the lineup over here. So some of the projects that we've worked on include One Wall Street. We've worked in multi-family residence in the Bronx, office buildings on Amsterdam Avenue, a whole variety, hospitals, a variety of projects and buildings throughout the New York tri-state area. So let's get started on the subject at hand, which is modern boiler room concepts and components. For over 15 years, the design and equipment, Bell & Gossett has led the education in the industry, and the little word schoolhouse was the leading educational entity for the United States for hydronics. And in that tradition, we'll continue. And today what we're going to cover is the basic theory of hydronics, hydronics components, what they do and how they work together, piping concepts, zoning concepts, expansion tanks and sizing, pumps and pumping options, heat loss, and boiler options. And last but not least, control options. And also we're going to cover water quality, which is very important and a subject that is unfortunately not ignored and can make a big difference. So let's start off with the basics. What is hydronics? Hydronics is the art and science of providing the right amount of water at the right temperature to the right area to furnish the right amount of heat or comfort for those who are in the building or the space that's being occupied. Okay, let's ask you a question here. True or false? Hydronic heating systems offer the maximum amount of comfort and efficiency possible to their owners. Well, that's actually false. What is true is that a properly designed and installed hydronic systems offer the maximum amount of comfort and efficiency. So that's the key thing. It needs to be properly designed and properly installed. Any improperly designed or installed system have the same problems. They'll have hot and cold areas, large temperature swings, and they'll have inefficient operation. And that's why we're here today to learn the right way to design and install modern hydronic systems. So let's get started with the basic theory. We always talk about BTUs, but you ever wonder where that came from? It came from a British engineer named Thomas Treadgold. He wrote a book called The Heating and Ventilation of Buildings. Actually, he wrote quite a few books on a variety of subjects. He was really way ahead of his time as a leading practical applications engineer. And he determined that a British thermal unit should be the amount of energy required to raise 1 pound of water 1 degree Fahrenheit. So 1 gallon of water weighs about 8.33 pounds. And to get BTU from that information, what we'll do is we usually deal with BTUs per hour. So 8.33 times 60 minutes gives us 4.998, which we're going to round off to 500. We're going to be using this 500 a lot on the next few slides, so you can understand where that came from. The gallons per minute times the change in temperature, called the delta T, times 500 will give us the BTUs per hour. So what is delta T? Delta T is a term we use to express the difference in temperature. For instance, if we have water entering a radiator at, say, 180 degrees, and it leaves the radiator at 175 degrees, we've had a 5-degree delta T. Gallons per minute times the delta T times 500 gives us the BTUs per hour. So 30 gallons a minute times 20 times 500 equals 300,000 BTUs. If we had a 20-degree delta T in a heating system, and our flow was 30 gallons a minute, we would deliver 300,000 BTUs. Now, if you think about that, we can also work that backwards. If we have 300,000 BTUs, and 20 times 500 was 10,000, so we divide by 10,000, we would get 30 GPM. The point being that if I have 300,000 BTU boiler, I need to flow at about 30 degrees, 30 gallons per minute in order to get a 20-degree delta T. So that's the factor. 10,000 is the factor that is consistent with a 20-degree delta T, which is most common what is used in traditional heating systems. However, if we need a less of a delta T, that factor would then drop to 7,500. Or if we went to 25 degrees delta T, to 12,500. And 30 degrees delta T, which is a little more common in today's modern applications, would be 15,000. Now, how do we determine these factors? Again, that 8.33, which is the weight of a gallon of water times 60 minutes times the delta T, gave us the BTUs. So therefore, 8.33 times 60 rounded up to 500 times 25 gave us 12,500. Similarly, times 500 times 20 gave us 10,000. And really, that's the most important one to remember is a 20-degree delta T, as that's the most common factor in determining the necessary gallons per minute to deliver the BTUs. So basically, if I have a 100,000 BTU boiler, I'm gonna divide by 10,000. I'm gonna flow at about 10 gallons a minute. So there you can see the relationship between flow and gallons per minute. Just keep in mind though, as we're talking about flow, we also have a pipe there, and there's only so much water we can move through a pipe without creating noise. It's pure physics, but it's also common sense. I mean, frankly, you couldn't fit 10 pounds of sugar in a 5-pound bag. So there comes a point as you're trying to flow this water through a pipe, it just becomes A, impractical, and B, it's impractical, and it's also just becomes noisy and unruly, and eventually it just won't flow unless you have a super pump to pump it. The circulator will continue to try, but it probably won't work. So let's talk a little bit about the pressure inside, because so we've talked about the flow in the pipe, and there's also a relationship we need to talk about is the pressure. So let's go back to another definition. If we had a cylinder that was 1 inch not in diameter, but 1 inch square, it's added up to exactly 1 inch square, and we put 1 pound of pressure, and this was a U-tube cylinder, it would move the water up 2.31 feet. So 1 pound per square inch, 1 pound of pressure per square inch will raise the water 2.31 feet. So the static height in feet divided by 2.31 plus 4 psi will give us the proper fill pressure. So what does that really mean? Is that if I have if I'm looking to fill a system up, and I know what the static height is, say the building is 18 feet high, so I divide 18 by 2.31, that'll be the PSI, and then I add 4 PSI extra, and that'll give me the proper fill pressure. So a foot of water column exerts a pressure of 0.433 pounds, approximately half a PSI. Basically, that's 1 divided by 2.31. So the rule of thumb for pipe sizing, when sizing the maximum flow rate that will fit through a pipe without making velocity noise, the pump head will be 4 feet for every 100 feet of piping. That's an important rule of thumb. So piping capacities, if we have a 1/2-inch pipe, okay, 4 feet of head for 100 feet will give us approximately 1.5 gallons a minute, or 1.5 gallons a minute, once again, times 10,000, will give us 15,000 BTUs. Similarly, 3/4 piping will give us 4 gallons a minute, or 40,000 BTUs. 1-inch pipe will give us 8 gallons a minute, or 80,000 BTUs. 1.25-inch pipe will be 14 gallons a minute, or 140,000 BTUs. An 1.5-inch pipe will be 20 gallons a minute, 200,000 BTUs. 2-inch pipe, 45 gallons a minute, or 450,000 BTUs. You can get that information to find the flow from Bell & Gossett's system sizer, which is available on the iPad and iPhone and Android. You get it from the iTunes App Store or from the Android store. We also have a plastic wheel that you can use. If you're interested, you can contact Wallace in his office, and we'd be happy to get you a plastic wheel. What it does is it'll also cover the other pipe, the flow and calculations through pipe at a given, I should say for a given pipe size, the flow rate through the pipe, and it'll give you the pressure drop for that and the velocity through the pipe. And that's really useful information. It's available, like I said, on your iPhone. It's and also through a manual wheel. Let's take a look at let's talk about the boiler now. You're going to start going into hydronic components. Now that we've covered the basics of what is hydronics, what is a flow, what is BTU, how to calculate the amount of flow that we need for a given boiler, let's start talking a little bit about the components now. And let's begin with the biggest, which is the boiler. We'll also cover the pumps, the expansion tanks, pressure reducing valves, flow valves, air elimination devices, and a pressure activated bypass. And let's begin with the boiler. We want to consider sizing the boiler, domestic hot water requirements, venting options, and available space. Also, we want to think some of the reasons, why would we be putting in a new boiler in a given building? It could be because the boiler's failed. It could be because we're looking to save fuel. It could be because we need to comply with emissions requirements. So let's take a look at some boiler room retrofits. Here's an old boiler that you might find in a building somewhere in the city, or on Long Island, or in Jersey, or in Westchester. And what you're going to find is you got high flue gas losses going out. You're going to have inefficient system controls, high levels of emission. Also, these old boilers, you know how warm they are. They're radiating. There's heat going out all along the sides of the boiler. So there's really surface and standby losses, and they can be very significant. And let's face it, to keep these guys running, very high maintenance cost. So if you have a boiler like that, why did it fail? Well, it could simply just be too old. Parts wore out, just became unreasonable to keep this thing running. They were constantly, remember, this boiler is constantly getting it's got water flowing through it, and it also is getting hot and cold, so you have thermal stresses and mechanical stresses. You have a fire side, you're going to have corrosion that can build up. You can have flue gas condensation. When that flue gas condenses, it leaves acids in there, and those acids eat right through the metal. You can have chemical contamination of combustion air. You could be pulling in air from the outside, could have contaminants in it, which then burn and they spread and they fill up and as residuals on the side of the fire chamber and along the exhaust. You could have water side damage. You can end up with scale buildup. That's very common. I'm sure any of you guys who've been out in the field find that all the time. And then the corrosion, of course. So when is it time to retrofit a system? Well, we can say when either the heating boilers fail, the age of the equipment, the boilers wear out, when maintenance costs are constantly increasing, and if we're just looking to save fuel and save money on fuel, increase our energy efficiencies, we might want to switch from oil to gas or from electric to gas, or we may desire a dual fuel system to make sure that, you know, depending upon the price of various fuels. And how should that retrofit take place? Well, only by fact-finding and investigating the entire system, not just looking at the BTU capacity of the boiler, but really to consider the entire system and the entire heating system of the particular building. We have to consider there are other possibilities and opportunity. We could either be doing a retrofit, it could be new construction. We want to consider the system water temperatures. What is the delta T, or the change in temperature? You know, we talked before about having a 20-degree delta T being critical. In new systems, we may be looking for 30 or 40-degree delta Ts. They may be more applicable, and there's big advantages to that too. Occurrences, but you can also have different loads at different times of day. The structure of the building, there could be solar gain, there could be particularly cold areas. You have to consider also the actual geometric structure of the building. We would probably really want to consider putting a lower temperature system design. The advantage of that is the lower the water temperature, and where we can still continue to heat the building, provides an advantage of allowing a modern condensing boiler to operate in a condensing zone, which means that as long as the return water temperature is below 140 degrees, it'll allow that boiler to condense, which means that it will be operating at very high levels of efficiency. We want to consider the system piping, looking to optimize the efficiency of the piping system. And we want to consider the electronic control systems, how the control systems are going to work, and how to utilize them to our best advantage. We also want to consider system integration to operate. Perhaps there's a building automation system there. We want to consider integration into the overall system building's operating system or integral management system. So let's consider some integration possibilities. So with hydronic heating systems, the radiation medium that we could be using may be baseboard, could be radiators, floor heating. We could have pool and spa heating. We could have rooftop fan coils. We could have domestic water heating, ramp snow melting, garage fan coils, in-suite fan coils, and we may have some supplemental electric heaters, and we're looking to eliminate those electric heaters. Also, today, when indoor air quality is key, we may be looking to bring in fresh air and maybe be looking to preheat that fresh air. So as we're putting the system back, you want to think about how the modern system is going to provide a savings for the owner.
Coffee truck is here. Coffee truck.
And let's consider what the project will save. Here's a project that we worked on. This was Fairfield Commons. We used Lochinvar night boilers, and we considered the present value, a cash flow analysis. The initial investment was $85,000, and we considered it by when we were putting the night boilers in there and what over the life expectancy of, say, 25 years, what the total cash flow would be. And as you can see, if you look on the far lower right, if they use the present value of money for a Lochinvar system with an $85,000 investment, would be about $329,000 over the 25-year life expectancy. Now let's consider if they kept the same equipment in the same building. There'd be zero upfront investment, but they would have elevated fuel costs in addition to the maintenance costs that are continuing to rise year after year. That same project, should they opt to not make a change over 25 years, would have a cost of about $1.35 million. So you take a look at the payback, you can see that although you have an initial investment by the Lochinvar night, there's a savings over time, and a rather substantial savings over time, in excess of $1 million over the life expectancy of the building. So one can see that if the cost, the actual costs, the life cycle cost, you can see with the dark blue line is what the actual cost of of replacing the boiler plant versus keeping the existing plant. So there is a substantial savings, and there are real economic motivations to modernizing a boiler room. And the spending, you can see the actual costs. Although they start up high with a Lochinvar system, they continue to decline over time. Whereas maintaining the existing building, those values will soar over time. And the return on investment for the initial investment is actually 47% over the life of the boiler. Not only that, not only are we just limited to an economic saving, but we also have there are savings in emissions. This is the level of NOx that exit over a year. There's a dramatic savings in that. Carbon monoxide, a dramatic savings, and carbon dioxide, also a dramatic saving over time. And just looking at the difference between the old boiler plant versus the new boiler plant, you can see the aesthetics alone can clearly make sense. But when we were evaluating that system, we had to look at the building and consider what was happening. And we had to think about heat loss. So what is heat loss? Because that's what we're providing heat to a space, and really we're looking to compensate for the amount of heat that's being lost. It's the rate at which heat leaves the building. And it also depends on the conditions. And from that information, that's how we size boilers, and that's also how we size radiation. So first thing you got to consider, let's take a look at New York City. So typically when we design in New York City, we choose either 10 or 0 degrees as a design temperature. So we build a heating system at 0, so for example, to heat a space when it's at perhaps 0 degrees. If you look at this is bin data from ASHRAE showing the amount of time that is spent, the amount of hours that are spent at various temperatures in New York City. Consider what they show. The design conditions rarely, almost never occur. A cooling mode is only about 10% of the time. The majority of the time is on a heating mode. So often if we design the system around a cooling system, it's actually backward. We should really, out of 8,000 hours of heating, design conditions occur less than 100 hours. That means 99.9% of the time, the building can be heated with less boiler or less radiation. So how do you do that? Well, you can put in smaller boilers, or you could put in less radiation. But if you put in smaller boilers with less radiation, what's going to happen? You're not going to, when you do hit those conditions, those design conditions, those few hours, that 100 hours or so, it's going to be mighty cold. The better option is to lower the water temperature. So let's take a look at heat loss. This is a analysis of, say, of a home and various rooms, and they look at the BTU heat loss for various rooms. And as you look at this is a typical IBR schedule. When you're calculating heat loss, you take each room, the design temperature, and the square footage of each room, and you get the heat loss for each individual space. You sum it all up, and as you can see, you get a total heat loss of about 23,593 for an outdoor design temperature of 0 degrees. Now, if the outdoor design temperature was actually not 0 degrees, but say 35 degrees, which is still cold, but it's not 0 degrees, the heat loss then drops from 23,000 to 11,797. That's a pretty dramatic change. So a 70-degree design difference, actually, a 70-degree design difference, we might have 100,000 BTUB heat loss for a house, as you consider all, where everything is dissipating from. It's going through the walls, it's going through the floor, there's infiltration from the wind that leaves out the roof, versus a 35-degree design difference would only be a 50,000 BTU heat loss. And the reality is, when we go back to that bin data a few slides back, most of the time we're going to be in that 35-degree area. We're not going to be at that 0-degree area. So would we choose a 50,000 BTU unit or 100,000? Well, what we really want, would we want to put a boiler in? How many boilers do we put in the room? Do we put 2 50s? Do we put them all the same size? Do we oversize? Why? What we would do is we want to consider something that modulates. We want something that's going to be able to provide 50% of to operate at 50% of the desired amount of heat, or at 100%. And that's what modern boilers do. And for example, Lochinvar makes an entire line of products like that, including the Noble, which come either fire tube as combis. They also provide domestic hot water, or they provide space heating, or you can get that they come in 3 models, either 110,000 BTU, 150,000 BTUs, or 199,000 BTUs. They're all made in the United States. Small footprint, 10-year warranty, 10-year heat exchanger warranty, 5-year parts. Similarly, they make a boiler-only unit, which provides 80,000 BTUs, 110,000 BTUs, 150,000 BTUs, or 199,000 BTUs. Also, all designed and engineered and assembled in the United States. Similar footprint, 24 inches high, 24 inches high by 17.5 inches wide. Again, these boilers will be able to provide, if you need 50,000 BTUs, they can modulate down at 50% to 50,000 BTUs, or they can modulate. They actually have a 10-to-1 turn down ratio. So, for example, 199,000 BTU unit can be put out as little as 20,000 BTUs or as much as 200,000 BTUs. Consider the night product line, which Lochinvar has made for many years now, probably about, I would say, 12 to 15 years now. And legacy-wise, they had the original nights were the KBNs. They had for the smaller units from 80 to 285,000 BTUs. They made the KBN XLs, from 400,000 BTUs to 800,000 BTUs. Those were their legacy products. They have since been upgraded and modified, first to the KHNs and then to the KHBs. The KHBs put out 55,000 BTUs to 285,000 BTUs. Those are the floor mount models. And those models feature now, they come with tremendous amount of features and benefits. Each time Lochinvar is committed to continuous product improvement. Part of this slide also is to show you that they have changed their products over time and metamorphosized them into making them more reliable and better, and using better technology and better engineering over time. Similarly, they also came out with a WHN, which is a wall mount unit, and also with a WHB, which is the new unit that features, amongst other things, better interface, pump controls, and very importantly, they come stock with a variable speed pump. There are big advantages to having the variable speed pump in that it allows you to condense over a wider range. For light commercial applications, they have the FTXL, 5 models, 400,000, 500,000, 6, 725, and 850,000. These units also recently that just came out, they came out with the new Night XL, which features a touch screen, 150 feet vertical venting. They also have 5 models for application: 400,000, 500,000, 600,000, 800,000, and 1,000,000. Lochinvar really has the broadest family of gas condensing boilers in the industry. You would find that especially with the Crest boiler. Those units come from 750 to 1,000,000 to 1.2 million, 1.5, 1.75, 2 million, 2.5, 3.5, 4 million, 5 million, and 6 million. So you can see Lochinvar has basically everything from a 50,000 BTU boiler covered all the way up to 6 million BTUs. And the beauty of them, they all have a smart system, which means allows them to integrate with each other, and they talk seamlessly to each other with simply a twisted pair of cables connected between the two. They will talk to each other and communicate accordingly and operate. They're allowed to be programmed so they can operate at optimal performance depending upon what the heating requirements for the space are. Let's talk about hydronic components. Now, we have a boiler. We consider the boiler. We consider the size of the boiler. We've already determined that we want to use, most of the time we need less boiler, but we have to design for that maximum point. So we want to consider using a modulating boiler, but with that, we're going to have a whole variety of hydronic components. Key to that is the pump. Let's consider what it does, how does it work, how do we size it, and what are the options in pumps? There are pump options. You can have wet rotor pumps and consider what the pump actually does. We're going to look at wet rotor pumps first. So wet rotor pumps moves the water heated by the boiler around the system to and from the radiator, fan coils, baseboard, or radiant floors. The flow rate is like consider it like a train that the heat travels on. Heat on the flow is like a commuter on a train. Some get off. All of the heat gets on the train at the boiler, and they all hop off at the radiators like commuters on a train. The slower the water moves, the greater the delta T. The longer it's out there, the more the heat gets off the train. So the pump, looking more at how it works, centrifugal pumps, which is what most pumps that are used in heating applications, they have a spinning of the impeller that gives velocity to the water. The velocity is captured in the volute that creates a pressure difference between the inlet and discharge sizes of the pump. Centrifugal pumps do not pull or suck water. High pressure, what happens is they're actually a pressure machine. They create a pressure differential. One side is low pressure, the other side is high pressure. And of course, water is always going to want to go from low pressure to high pressure, and that's how we create flow. Simply, water enters into the eye, it goes out the perimeter of the impeller, it creates a pressure differential, and that's how the water travels. Centrifugally, it exits out, and then it exits out the volute. And the force, this force is measured in feet of water, typically. So 2.31 feet is 1 foot of head. We always consider, when we specify pumps, we consider the flow, which is in gallons per minute, and the amount of pressure that is put out, which is considered feet of head. And once again, feet of head is 2.31 feet is 1 pound of pressure. Here you can take a look at a cutaway of a typical wet rotor pump. You have the impeller, bearings, a bearing system. In this particular case, this is a 3-speed pump, so it has a speed selector, a motor, and as you can see, this is a wet rotor pump, which means that the bearing, the rotor area, which is this area in here, is cooled by the water itself. There's a system to allow the water in there. So this is a wet rotor pump. Taking a look. Let me go back. I'd like to show you a wonderful video put out by Lochinvar, which is part of Lochinvar University. Something that I highly recommend that you get people join. And when we get to the end of this presentation, I'll give you the connection for Lochinvar University, but I strongly recommend it. Every bit of information about Lochinvar boilers, service, assembly, installation is covered in there, and including things like this wonderful video produced by Lochinvar.
Have you ever wondered? Slinging water away and creating the delta P, or difference in pressure.
Let's try that again. Okay. Can you hear that?
Have you ever wondered how a circulator moves water in a system? Today, we're going to cover these topics and more. These devices are actually very simple when you break them down. They are made up of separate parts. The volute is the body of the circulator. It is where the water enters and leaves the circulator and is the home of the impeller. The impeller is the part of the circulator that spins, slinging water away and creating the delta P, or difference in pressure, when the motor is energized. The motor is the electrical device that is connected to the impeller by a shaft and is responsible for turning the impeller. It's good that we know the anatomy of a circulator when we try to understand how they work. This image represents a circulator in a closed system. Most circulators will have test ports on the suction and outlet sides of the volute. But how do I know the suction from the discharge side? There's actually a very simple method. If you look at the bottom of the volute, you'll notice that one of the sides of the circulator is piped directly to the center of the body. This is always the suction side of the circulator. We know this because the impeller that is housed inside the volute begins to spin, and it creates a Venturi effect. You could imagine this as a mini hurricane inside the body of the circulator. The pressure at the center of the impeller drops, and the pressure on the outside of the impeller rises. This creates a delta P, and Mother Nature takes over from there. In nature, everything seeks equilibrium. So the higher pressure we have just created seeks out any lower pressure. The suction side of the circulator provides just that. This means the pressure coming out of the discharge side of the circulator seeks the suction side. And since we are in a closed system, it has a direct path back to the circulator. And now we have flow. It's really that simple. But how much flow are we dealing with? Do I need a fancy flow meter to determine flow? No. All you need is a pressure gauge and a pump curve. A pump curve is a chart provided by the pump manufacturer. This chart shows feet of head on one side and gallons per minute on the other. In the middle of the chart, you'll see one or more curves. These curves represent the impeller size of the circulator. Some charts will have multiple sizes shown on a single chart. Some charts will only have one curve. When reading pump pressure, you should only use one pressure gauge to read the suction and the discharge pressures. Different gauges could give you different readings because they may be individually calibrated. Attach the gauge to the suction side of the circulator and take a pressure reading in PSI while the circulator is running. Let's say we take a pressure reading on the suction side of the circulator while it's running, and it's 10 PSI. We then take a pressure reading of the discharge side of the circulator while it's running, and we have 18 PSI. We then subtract the discharge from the suction. 18 minus 10 equals 8 PSI. That is my delta P. Now I have to convert this to feet of head by using the constant. 8 times 2.31 equals 18.48. We can round this up to 18.5. Now we find 18.5 on the foot head side of the curve, and we make a mark. Then we draw a straight line from this mark toward the impeller curve. Once we contact the curve, we change direction, and we start heading toward the GPM side of the curve. Your GPM is determined by the point where the line intersects the GPM side of this curve. Also, just for your information, there is a constant for converting feet of head back to PSI. This constant is 0.434. So multiply feet of head by 0.434 to get PSI. Wow, we just did a little math and nobody got hurt. It is important to know how circulators work if you want to understand how flow is controlled in the system. Hopefully, you now have a better understanding of how that all works.
And that was part of Lochinvar University's training, and I highly recommend you visit there. I'll give you the address towards the end of the presentation. So how do we size a pump? Well, there are two main considerations. How many BTUs is a pump going to deliver? And from that information, we'll know what the GPM is, or the flow rate will be. And then how much resistance will the pump have to overcome to get the water where it needs to go? So when sizing a pump, the first thing we have to realize is that system flow is kind of like a Ferris wheel. The weight of the water going up equals the weight of the water going down. So really, in a closed system like a hydronic system, the actual height of the building has no effect on the amount of sizing of the pump, and the amount of head pressure that you need for the pump. Really, in this particular case, like the Ferris wheel, it only has to overcome the friction of the system. So when calculating pump head, we don't really care what the height is. What we really only care about is what is the longest distance of pipe that we need to get water to. What's the furthest piece of radiation? So with that, we add 50% to that as a rule of thumb for fittings. Keep in mind that, for example, elbows add 5 feet is the equivalent of 5 feet of distance. T's also add to it, as well do elbows and T's will add as much as 50%. So we just round that number off. So if we have a distance of say 100 feet, and then we add 50%, we then have 150 feet. We multiply that times 0.04, and that gives us the required head. So let's consider, going back to how we size it, let's do a simple example. If we have a zone with 50 feet of 3/4 inch baseboard rated at 160 degrees F, we would need 50 additional feet of piping. So 50 times 480,000 BTUs is 240,000 BTUs. Divide that by 10,000, that's 24,000 BTUs divided by 10,000 gives us 2.4 GPM. So we have 50 feet of baseboard and also 50 feet of additional piping to get to and from the baseboard. So with this example, the pump needs to deliver 2.4 GPM times, we had 100 feet, 50 feet of baseboard, times 50 feet of piping is 100, plus 50% is 150 feet, times 0.04 is 6 feet of head. And then we got 24,000 BTUs divided by 10,000 is 2.4 GPM. So we need a pump that's going to give us 2.4 GPM at 6 feet of head. Looking at that with this example, we need something that's going to deliver that. Here's a sample chart. These are from Bell & Gossett's 3 pumps here, the NRF22, the 33, and the NRF9. We plot that point. You can see we're above the NRF9, but we're below the NRF22 and the NRF33. So we could use either one of those pumps. Similarly, we have a 3-speed pumps. Here you can see some curves for the NRF25 at various speeds. The NRF36, it's at either one of its 3 speeds, in the NRF45. Once again, we talk about, as you saw in the video, the pump curve. We have a pump curve that comes with it. You saw those sample pump curves before. And then on the opposite direction, we're going to have what's called a system curve. So the actual point of the pump curve, where the pump curve meets the system curve, is the actual operating point of the system, where the pump curve and the system curve meet. Some other hydronic components with pumps include oil lubricated pumps, such as the Series 100 or the HV and that entire class of pumps. They have a motor, a coupling, bearing assembly, shaft, and a seal, and an impeller inside the volute. The oil lubricated pumps also, I shouldn't say similarly, but another good alternative. Oil lubricated pumps are something that predominated a long time ago. You still see them out there. They're still pretty common, but they're sort of changing. And they've switched to is to permanently lubricated pumps, which is a little bit different. There you have a dry motor, a rotor, seal, impeller, and bearing. These do not require annual lubrication, whereas the oil lubricated pumps need to be serviced annually and to be lubricated annually. And if you forget, they could wear out. These pumps are a very good alternative to the older pumps. The oil lubricated pumps is permanently lubricated pumps. Another option is when you get into larger systems, there is a Series 80, which is a larger pump. The EcoCircs, which are ECM pumps, which I'll talk about a little later. The 90, which is a closed couple pump, and a Series 60, which is has a 3-piece pump with a bearing assembly. The 90 and the 60s are similar, except one is a 3-piece pump, one is a closed couple pump. The E80s are larger pumps and for larger systems. And then we have what's for larger buildings, we have a variety of end suction pumps. What happens here is the water comes in this way and out the top, comes in the end and goes out the discharge. These are you have 1532s and 1531s. Basically, they're the same pump, except one comes with a larger base for support. The 1535, which is a smaller pump, typically used in various applications, cooling applications, and also for tank fill applications. And then the very, very prevalent 1510 pump, which is an outstanding pump. It's a long 24, 25-year life expectancy. And this pump is a 3-piece pump with a bearing assembly where you can change this, you can replace the seal and replace it without moving the motor or moving the volute. It's found in many larger buildings. A 1510 is found all over the city of New York and cities across the country. There are other pumping options too. You can get multi-stage pumps, especially useful when you need high head applications. For large flows and large applications, there are horizontal split case pumps, and of course, Bell & Gossett came out with the VSX pumps, which are also split case pumps, and they would allow you to for very large applications. They provide advantages, space-saving advantages for very large jobs, up to 15,000 gallons per minute. But what I'd like, most of what we're focusing on is smaller buildings here and residential buildings as well. And I'd really like to talk about electronic commutated motor pumps, or ECM pumps. If you haven't heard that term, you're going to certainly hear it a lot. This technology will use permanent magnets. There's no shaft, seals, or bushings. The only was one moving part, which is the in this particular case is the spherical impeller or rotor. It's all one unit. There's a stepless speed control, has a high efficiency ECM motor. ECM motors, what makes them different from standard pumps? Well, it really comes down to the motor. These motors will look the same as your standard induction motors, but the construction of the motor will be completely different. See, what we have, most of the pumps that you see, especially wet rotor pumps, are AC induction motors. They don't have a permanent magnet. The stator coils will create a magnetic field which induces current into the rotor, and then the rotor current interacts with the rotating magnetic field, which causes a rotation motion in the rotor. Because of the magnetic and electrical fields are out of phase, there's a little slip, and you need greater currents and greater current losses. AC circulators, they don't have permanent magnets. And electronic commutating motors, they have permanent magnets on the rotor. This inherently saves electrical power because you're not required to input some power in to induce the magnetic field on the rotor side for proper rotation. And AC circulators will always exhibit motor slip. There's always a lag, always a space. And this function of inducing the magnetic field that's part of the function of inducing that magnetic field on the rotor. ECM circulators will not have this, as the magnets are present on the rotor, and this gives ECM circulators the advantages of responsiveness to system changes. They have permanent magnet rotors. The magnetic rotor grabs onto the rotating stator magnetic field, causes rotation. And this rotation is controlled by a microprocessor, which keeps the stator current in phase with the magnetic pole of the rotor. Thus, you end up with much lower current requirements and no slip and much greater efficiencies. With this permanent magnet motor technology, the rotor is a permanent magnet, and the commutation of this process of pulsing power on and off to create a rotating magnetic field in the stator. As you can see here, as what's happening is as the stators are drawing, the rotor is being attracted to the various motors, to the various points on the stator. And inside, you need an electronic driver to control this commutation for the rotor rotation. So there'll be some electronics in pretty much all ECM pumps. And this controller energizes the stator windings in specific sequence to facilitate proper rotation. Yeah. For proper rotation, the controller must determine the rotor position, typically via a sensor or some means of positioning. Typically, they have some sensor on there to figure out exactly where the rotor is and to keep the stator in phase with the rotor. Here you can see a view of a typical Xylem's unit. You can see you have your impeller and pump housing and a stator winding, and inside you got your permanent fixed magnet and the support system, the stator, and you can see that there is a PC board which is controlling this just on the outside of the pump, towards the top of the pump. So a little bit about ECM pumps. How do we determine efficiency? Well, it's the desired output in quantity versus the necessary input quantity. Distribution efficiency for space heating systems then would be considered distribution efficiency would be the rate of heat delivery versus the rate of energy used by distribution equipment. So let's consider a system that delivers 120,000 BTUs per hour at design load conditions using 4 circulators at 85 watts each. We would have a distribution efficiency of 120,000 BTUs per hour divided by 340 watts. That gives us 353 BTUs per hour per watt. So this is like I said, we're trying to determine how well we distribute the heat within a heating system. So is 353 BTU per hour per watt good or bad? We need to compare it to something. So let's take a look at a furnace blower, which this blower operates at 850 watts and delivers 80,000 BTUs, which is typical for a furnace blower. Thus, its delivery efficiency would be 80,000 divided by 850 watts, or about it distributes the heat at about 94 BTUs per hour for watt. So if you compare the two, the hydronic system distributes the heat almost at a 4 times more effective method than a forced air system. Its efficiency is really effectively 4 times greater. So what that tells us is that water is dramatically superior to air for heat delivery. But even after considering that, is there room for improvement? Consider this beautiful house here, and we look inside the system, inside their heating plant, and you see all these circulators lined up. If we use ECM pumps, this hydronic heating system has, on this 10,000 square foot house, used 40 circulators, each consuming 90 watts. The design load is 400,000 BTU per hour. So the distribution efficiency is 400,000 divided by 40 times 90 watts, or 111 BTUs per hour per watt. Realistically, that's not that much better. 111 BTUs hours per watt is not much that better than 94 BTU hours per watt. It's actually in some ways almost the same as the forced air system. So how do we improve that? If we substituted small EcoCircs, these smaller pumps, they can be set to draw as little as 10 watts. So their efficiency is almost 10 times greater. When you consider that, the distribution efficiency would be from 400,000 BTU divided by 40 circulators at 10 watts, produces 1,000 BTUs per hour per watt. It's a tremendous increase. So we know that ECM pumps work. But what sizes of ECM pumps are available? Where do they fit? Well, we're pleased to announce that Bell & Gossett has come out with a brand new product. They call it the EcoCirc 2018 and the EcoCirc 2018 Plus. The EcoCirc 2018 it's the reason it's called 2018 because it has a maximum 20 feet of head or an 18 GPM or 18 GPM, 70 watts maximum power. Remember, all those other circulators were running at 90 watts. This is 70 watts at full load. Once again, we can modulate it downward, in which case it drops. There are 3 operating modes in this. We can set it for proportional pressure. What proportional pressure does is, let's assume we have a system where we have, for example, Danfoss valves on something. as those valves open and close, the required pressure in the system will change. As the pressure changes, say the speed of the pump will change. If the pressure increases, the speed of the pump will then drop. It'll maintain that pressure proportionally. It'll maintain the flow proportional to the pressure. That's what proportional pressure is. You can also set it for constant pressure. We can maintain, it'll speed up or slow down to maintain constant pressure through the system. That's an application that's used, for example, in pressure boosting, where we're providing water to a system. We want to maintain that constant pressure, or we can set it at constant speed with an adjustable speed control. It operates from fluid temperatures. It can be used for heating and cooling, as it has a range of 14 degrees to 230 degrees F. And it comes with a Circ Guard, which is it's an integrated system that allows for purging of air and prevents deadheading and other system problems. And that is something also that's going to be more sophisticated with time. As time goes on, Bell & Gossett will be integrating Circ Guard and other components as well to allow the pump to adjust to the external variables of the system. But right now, what it does is it also helps assist in air elimination, because it has an automatic air purge to remove any trapped air in the pump. It has one knob, one turn knob, and a multicolor LED display for easy reading. It has and also for setting up the pump. A chalk valve is included in the box, and it also comes with an insulation cell. The ECM EcoCirc Plus 2018 comes with all its standard features found in the EcoCirc 2018 Plus. It has Bluetooth communication, and what's really useful is a 0 to 10 volt input, which allows you to connect to any boiler that has 0 to 10 volt signal, and will allow the pump to modulate based upon that input signal. Also has temperature control, and also has an eAdapt auto learn and night mode. It'll adapt basically on applications, knowing based on the time of day. It has also a digital display. Again, and also the information can be read with an app downloadable from Xylem. As you can see, you can take a look at the curves for these pumps. They operate, once again, from 20 GPM, from 20 feet of head out to 18 GPM. As you can see, the proportional pressure, if you set it for proportional pressure, it starts to, as the pressure increases, the speed will start to decrease, and a constant pressure curve and a fixed speed curve. But if that's not, you have larger applications. Bell & Gossett makes an outstanding line of large wet rotor pumps called the EcoCirc XL. These pumps also feature ECM motors. There are 13 models that go up to 375 GPM. They also have 4 control modes: proportional pressure, constant speed, and it has also automatic night mode. Comes standard with BMS communication, Modbus, and BACnet, and can also communicate with a laptop. These large wet rotor pumps are high performance pumps. They take efficiency to advanced levels. They use ECM permanent magnet technology. They feature state-of-the-art hydraulics and advanced motor design and truly intelligent controls. They have a display. You can actually read the flows and head. You can adjust the pump. I've used them where you can actually adjust the pump for exactly the amount of flow that you desire. You can see exactly how much energy consumed in watts, all readable directly from the screen. It delivers the right performance across a broad range of head and flow requirements due to the variable frequency drive. It comes in cast iron. Actually, that's a mistake there. It's no longer bronze body. They are stainless steel pumps, and they're used for heating, cooling, and potable water applications. In potable water applications, we have stainless steel pumps where you can built in, you no longer need an aquastat. You can set that pump to modulate based on the temperature of the water. It has a built-in temperature sensor. You can take a look at some of the ranges of these pumps. They have high head performance ones that go up to 70 feet of head and out to 150 GPM, and then also units that produce large flows with relatively lower head pressures. Taking a look at the makeup of these pumps, they come with an insulated shell that comes with the box. The housing is either cast iron or stainless steel. It has a self-flushing membrane for heat, restricts any abrasive particles. Has a high tempo ring, shaft, hardened steel, stainless steel shaft. Its impeller is glass-filled polyethylene sulfide, or it'll be 3/16 stainless steel. And the wetted parts are all 304 stainless steel. The ECM permanent magnet and motor housing is aluminum. And as you can see, the control is all connected here with half-inch NPT electrical fittings. This unit can also be separated from the pump itself. The key benefits of the EcoCirc XL: you get the benefits of an electrically commutated permanent magnet motor. It has an integrated variable frequency drive, infinite speed regulation, several operating modes to suit various field applications, constant pressure, proportional pressure, constant curve. Then you have an analog speed control with a 0 to 10 volt signal. You can also have a delta P and delta T control with external sensors. You can add an external pressure sensor, or you can add an external temperature sensor. So you can actually modulate this pump based on changes in temperature or changes in pressure. It has nighttime setback features to put the pump in sleep mode during low or no load conditions. It's simple to install. Its commissioning requires no specialized programming. The pump data is adjustable with an interface panel. The motor is rotatable in 90-degree increments for easy access to display. The illuminated display makes it visible even in dark areas. It's perfect for new and retrofit applications and energy upgrade applications. And also the PL series, those the permanently lubricated series, the 3-piece boosters, and the series 60s and 90 products are easily interchangeable with the EcoCirc XL models. Just taking a look at the modes of operation, you can see there's constant pressure, proportional pressure, constant curve, and night setback. Those control modes are all standard and accessible from the front interface. The delta P and delta T modes of operation, you require a computer interface in order to access that. In the constant pressure mode, it maintains constant differential pressure at varying flow rates until max speed is released. Desired pressure can easily be set by the user interface. Its default operating mode. It's sensorless. This is all sensorless. It uses an algorithm to calculate exactly what its pressure is. It does have a sensor in there. It's recommended for use in systems that have smaller constant pressure losses. Good example is radiant heating and cooling. Proportional pressure. Pump pressure continuously adjusts based on flow rate. The pump head decreases as flow rate decreases. Maximum pressure is easily set from the pump interface. It has, again, sensorless algorithm, or it can be used with an external sensor to create a deep delta P, a change in pressure sensor. It's recommended for use in systems when pressure varies with flow rates, as in hydronic systems using zone valves. And constant speed, pump can be set to maintain performance. It'll maintain a fixed speed at any flow rate. The pump head increases as flow decreases, and the speed can be programmed at the pump or a user interface. The constant curve is great when using the primary or boiler loop or in a primary secondary hydronic system. Constant temperature. The pump will vary the speed to maintain temperature. It has an internal or can use an external temperature sensor. And the constant temperature can be used to maintain the zones to supply the water temperature. Differential temperature. In this mode, the pump maintains constant differential temperature at any flow rate. It uses internal and external temperature sensors. The differential temperature can be used to maintain a desired delta T in a zone to better control the return water temperatures. Controls adjust the differential pressure set point as measured by temperature varies. This is delta P/T. Internal and external, it requires you can either use the internal or use an external temperature sensor. It has a sensorless algorithm or uses an external delta P sensor. It's recommended for use in systems with varying supply water temperatures. A night setback. Pump responds a night setback as controlled by other means in the system. It reduces pump power consumption to the minimum when heating load is not required. Good example is evening and nighttime when the building heat requirements are lower. And you can use this feature in conjunction with the constant pressure, proportional pressure, or constant speed applications. One thing that's really cool about this pump is it can has two pump operating modes. It can either have a backup operation where the lead pump runs while the second pump remains off and will only turn on if the lead pump fails, or alternate operation when only one pump runs at a time over a 24-hour period, after which point it will power down as the other pump comes on and begins pumping. In case of pump failure, the other pump takes over. Often we use these when you have two units and you want redundant pumps. We set these in alternate operation. It's standard. You require no additional. You don't need a pump sequencer or anything like that. It's all built into these pumps. It saves it really saves you getting a pump sequencer, and it talks intelligently, but simply weren't running a twisted pair between the two. You can also run this in parallel operation, where the lead pump runs to satisfy the demand. If it can't satisfy the demand, the follow-up pump will run in parallel with the lead pump at the same set point. This only works in constant pressure mode. And then forced parallel operation. The leader and follower run at the same speed to meet the demand. You can interface with these pumps either using a RS-485 cable, and it connects with an application that's available free of charge from Xylem. Or you can also use it in wireless module. Doesn't require any software. You just need a web browser. And you put the wireless module in there. You link up to it with your phone, and then you use a browser for controlling all the parameters on the pumps. It's pretty simple. There's a code on the side of the pump. Plug it in. You're ready to go. Now, one of the things we talked about was the 0 to 10 volt application for these, and I said that it could work in conjunction with the boiler, modulating the boiler down. And here's a really, really important concept here. So we have flow boiler pumps with a modulating boiler, and what happens is when we have a fixed flow pump, we set it for a firing rate of typically 100%. So for example, here we have a 500,000 BTU boiler, which runs at about 93% thermal efficiency. Let's assume it has a 5-to-1 turn down ratio. So the output is 466,500. At a 20-degree delta T, we would have 47 GPM going through that. At an 80% firing rate, we'd have 373,000 BTUs, but we would still be moving the water at 47 GPM. The delta T would then drop to 16.22. At 60%, 280,000 BTUs goes out, and it puts a delta T of approximately 12 degrees. Then just to take a look at 20%, the output is 93,000 BTUs. It's only going to have a 4-degree delta T. Now, if we modulate the speed of the boiler pump to work in conjunction with the rate of flow of the boiler, here you can see at 100% flow rate, we would have the GPM would be at 47. We'd get 20 degree delta T. As we go to 80, we would drop the GPM to 37 GPM. We would maintain 20 degree delta T. At 60%, again, 27 GPM, we slow down the speed of the pump and maintain a delta T. Same thing is true at 20% operating. We drop the speed down to 10 GPM, we maintain a 20 degree delta T. Well, what's the advantage to that? Why does that matter? Well, consider that boilers will only condense if the return water temperature is below 140 degrees. So at this point, if we have a temperature, say an output temperature of 150 degrees, we go backwards and we only have and we're running at 20%, we only have a 4 degree delta T, we're going to be returning water at 146 degrees. That is going to make that boiler is not going to condense. That efficiency is not really going to be 93.3%. It's going to be something less. It'll be probably in the 86, 87% range. Here, with the modulating, as we speed the boiler down, maintain that 20 degree delta T, we're going to be returning the water at 130 degrees. And the advantage of that is that boiler will continue through its entire operating range, will continue to maintain condensing conditions. So that's the really big advantage of having ECM pumps work in conjunction with the modulating boiler. It is such a big deal that on all Lochinvar Night residential boilers, the new units, I believe they call it the KHB and the WHB, all of those come standard with an ECM pump and a 0 to 10 volt input, which wires directly to the boiler, so that you maintain that constant, you maintain that constant delta T that you've so designed into your system, and therefore the unit will continue to modulate through its entire operating range. Okay, let's start talking about other hydronic components, and let's consider the expansion tank. We've talked enough about pumps, I think, at this point. So the expansion tank, what does it do? Well, and what is it? How does it work? How do we size it? And where do we put it? What does it do? Well, raising water temperature in a system, in a heating system, from 40 to 180 increases the volume of water by about 5%. The expansion tank absorbs this thermal expansion. That water needs to go somewhere. If this provides a spring, it maintains a minimum pressure set inside the system. Keep in mind, water does not compress. So that added volume is going to have to go somewhere, and that's what the expansion tank is for. This is the tank before installation. We set the system's initiating operating pressure, and then at maximum pressure and fluid temperature of the fluid. So you can see that when as the system initially starts, it expands a little bit, and when it's at a maximum temperature, it'll expand more. The air and the water pressures must match before the system is filled. So you need to set the pressure level of this pressure level of the expansion tank before you connect it to the system. This chart assumes a pressure of 12 psi. Relief valves are set at 30 psi and the average system temperature of 200 degrees F. So here is an expansion tank sizing guide. Okay, this is a good rule of thumb. You have 150,000 BTU boiler with baseboard, you can use a 30. If you go to 200,000, you want to go to a 60. There are other types of tanks. There's compression tanks. You'll see them on older jobs. I haven't sold one in almost a decade, but you do see them on older jobs. You see them existing. What happens is they tend to be replaced with bladder tanks. They're the most common. And then you can also get commercial pre-charge tanks. The bladder tanks, as you can see here, basically has a bladder inside the tank. It can expand to the size of the tank. Bladders can be full acceptance, where the volume of the fluid will hold is equal to the volume of the entire tank steel shell, or they can be low acceptance bladders, where the bladder can hold less than the steel shell, and it's used where safety and system pressure are a large concern. Compression tanks, I'm going to tell you, they're not used. Like I said, I haven't sold one in over a decade. You see them on job sites. Basically, you want to look to replace them with bladder tanks. The expansion tank. Now, where do we place it? The position of the tank is the point of no pressure change. That we have maintained with that the purpose of that tank is to maintain part of the purpose of that tank is not only to take up the volume of the expansion of water, it also doesn't change that point. The pressure never really changes. So the system should always be after that tank. So you're pumping away from the point of no pressure change. Here you can see the pump is now put on the away from the expansion tank. And the reason why we do that is that if we put the tank on this side, then we would create, remember what we said? We said that the pump is a pressure differential machine. It creates a differential of pressure. So if it starts to drop, it could create vacuums along here and suck air into the various components. So that's the reason why we always want to be pumping away from the expansion tank. That's a big takeaway from this, is always be pumping away from the expansion tank. Here's other hydronic components. Here we have this is a complete boiler hookup kit offered by one of our manufacturers, Xylem. It consists of an air elimination device, a micro deaerator. It comes with a nipple for easy connection, a couple of isolation valves, a boiler fill valve, the expansion vessel, and the backflow preventer. Let's talk a little bit about the pressure reducing valve. It's also known as the fill valve. And when it's supplied with a relief valve, it's also known as a dual unit. It allows the system to install the fill pressure at the required pressure. It usually comes preset to 12 psi. It's adjustable. Reason why the pressure relief valve, once again, if you take a look, 2.31 feet per pound times 12 psi means that it'll raise the water 27.71 feet. Okay, so when you consider in a typical house, the boiler's in the basement, the highest radiation is on the second floor. You measure the height from the pressure reducing valve to the highest point of the system. This is known as the static height. You divide that by 2.31. In this particular case, you got 18 feet. Divided by 2.31 is about 7.79, or rounded off to 8. Add 4 psi to make sure that you have a little extra pressure in there, also to eliminate any air at the highest point. And guess what? You get 11.79, or roughly 12 psi. That's the reason why the fill valves come pre-charged and preset for 12 psi. If you had an additional floor, so instead now the static height is now 29 feet, then you divide that by 2.31 and you would get 12.5 psi. Add 4 psi to that, you're going to get 16.5 psi. We would want, if we had an extra foot, we'd want to adjust it for 16.5 psi. Once the pressure is set and it's filled to the proper pressure, you should shut the valve off before the reducing valve. That protects the boiler from what it protects. But if you do that, very few people do. Most people leave that fill valve open. What protects the boiler from dry frying if there's a leak? Well, that's what the PRV is not designed to protect the boiler. It's really only there to set the correct system pressure. That's its job, the pressure relief valve. It's the low water cutup's job to protect the boiler. Let's talk about flow or check valves. There's a couple of choices there. Why do we need flow control valves? Well, it's not really to control the flow. It's really to prevent overheating and crossover. Inside a pipe, gravity flow will occur when a pump is off. Cooler water will fall, warmer water will rise. This can cause overheating of zones that are off. What will happen is if we don't have any flow control valves, the gravity of ghost flow when we're heating one zone can switch over to another zone. Or for example, in the summertime, if you have an indirect fired water heater on your boiler, it can then transfer the heat it can transfer the ghost flow can actually send the water into the regular heating system. So gravity can occur in two pipes, and it can be where the return can actually be hotter than the supply. So that's why we put a flow check valve. So you can actually have this reverse flow going in there. The flow check prevents that from happening. Bell & Gossett offers a whole variety of iron body straight and angle pattern units. They can either be connected straight or up through the bottom. Either way, they come from 3/4 to 2 inch. They have a straight pattern for 3/4 inch. They have the angle pattern at 2.5 and 3 inch, and a straight pattern also at 2.5, 3, and 4 inches. We also get check roll flanges. So they have a flow check built right onto the flange. It comes in 3/4 inch and a half IPS and sweat. It's compatible with most pumps. And also we have hydrotrol flow control valves. They have turn opens the valve, IPS only. These units only come in IPS. They come in 3/4 inch, 1.25 inch. They can be installed vertically or horizontally. Let's talk about air elimination devices, the next hydronic component on the list. We have inline air scoops, very simple, from inch to 3 inch, very simply slows down the velocity, allows the air to go out the top. You can have an enhanced air separator, which operates with that same principle, but also has a device in there, a coalescing medium that allows it to separate the bubbles and allow the air to separate a little bit easier. And then we make a small versions of that 3/4 to 2 inch called the EASP Junior. How do they work? Well, as water enters the air eliminator, it slows down. There's a bigger space there. The velocity is coming in fast through the pipe. It slows down in the space. It allows the trap air to rise to the top, and it's released at the opening. Here you can see a quick little diagram. Another device that we also use for air elimination, especially in radiant systems and systems in general, are primary secondary headers. They perform the same function as a closely spaced T, but also give the added advantage of acting as an air elimination device as well. And also you can see that it'll be the units that come from Bell & Gossett come with an air vent and with a drain valve, which allows you to eliminate any debris and rust and debris that's been fixed into the bottom of the air separator. Their sizes are basically from 1 inch to 1.5 inches in IPS and flange from 2 to 4 inches. For larger ones, we can get those from Wessel's Manufacturing, and we can also fabricate them, as you can see here, with custom sizes and configurations. Here you can see a specialty one that was made to fit in a specific geometry. This is made out of Aquatherm polypropylene piping. It's made to operate for a heating system. Primary secondary headers, as you can see they're out. You can see their utilization here. Here you can see we have closely spaced T's here. We can substitute it with the primary secondary header. Another thing that we need is also we use a lot of is a differential bypass valve. It's when the system varies due to the zone valves are opening and closing. In the event that all the zone valves close, at this point you would have a bypass which allows the water to flow once the pressure exceeds the pressure setting on the differential bypass. It eliminates velocity noise by excess flow in the remaining circuits. And it is not necessary if you're using an ECM pump or if you're using an ECM pump or you're using a variable frequency drive. Here you can see the differential bypass is connected between the supply and return, and is jumping the pump. One of the things we also use in systems, especially on large pumps, is a triple duty valve. Typically, they are connected to the discharge size of the pump, and they provide 3 functions in one device. They're a calibrated balancing valve, they're a spring-loaded check valve, and they're an isolation shutoff valve, hence the term triple duty valve. Triple duty valves come in a wide range of sizes. They come in a straight pattern flange from 2 to 14 inches, groove from 2 to 12 inches, and balanced straight patterns from 3 to 16 inches. We also get angled pattern flanged units from 2 to 10 inches, and smaller units in like you see over here, this in NPT and rotatable flanges from 1 to 2 inches. Take a look at how they work. You have a brass disc with a soft seat, which provides a positive shutoff and non-slam check valve. You got a calibrated nameplate, and you can end up with integrated ports for easy delta T measurements and delta P measurements too. Another thing that's used, especially these are used almost all the time with end suction pumps, and also sometimes with larger systems. And one of the things we often use is the end suction diffuser. What that does is it conditions the flow of the pump to ensure the highest pump efficiency retention. What that means is that effectively, if the water's coming in turbulent, it'll tend to create a laminar, so that at the suction side, the flow can come in, and flow can come in laminarly and a nice smooth flow, so the pump can operate at its maximum efficiency. It enables the pumping system to function at the most optimal performance parameters, and typically, especially in large systems, you need a minimum of 6 pipe lengths. So if you have, say, a 5-inch line, you'd need 20 inches of straight pipe before you can make a turn. With this, you can make it much tighter, and it reduces space requirements, and it also improves the performance of the pump by making sure that flow is laminar. Comes in white, and once again, those units come in larger sizes, up to 10 inches. Here you can see the typical application where you have a suction diffuser and a triple duty valve. Like I said, these are typically used on end suction pumps like the 1510. Okay, let's think about this. Now we have these components, and one of the things that happens is we get to the water quality, and it's often an ignored factor when putting together and designing a hydronic system and operating a hydronic system. We can have chemical additives, and we have filters. Inside, as you can see, these are just some sample pictures of pipe. You can imagine how this has dramatically changed the flow. Take a look at this pipe on the right. When this system was designed, the pump was selected to operate at a certain flow rate, giving feet and head. Well, you can be sure that when you get all this corrosion around the outside of the pipe or the inside of the pipe, the corrosion is going to dramatically change the flow characteristics and the head characteristics. Now, that pump, which is originally specified specifically for this system, is no longer going to behave properly. And then it causes all kinds. Not only do you lose efficiency, but you can also get failures. It's going to increase fuel usages, going to create dead zones. You get general corrosion. You get various failures, scaling. Look at this, the scaling, the blockages, biofilm, sludge, pitting corrosion. Poor water quality will reduce the heat transfer rates up to 15% and 6% boil efficiency in just 3 weeks. Low flow areas will cause dead legs, premature component wear and breakdowns. It is, we don't take it so seriously, but when you go to, in Europe, for example, the requirement for water treatment is so critical that water circulating systems, and this is right out of a European boiler manufacturer's installation and operation manual. All recirculatory water systems are subject to corrosion unless water treatment is applied. What's really interesting is you can say, you must add a suitable inhibitor to the systems, and all systems must first be flushed, and a suitable inhibitor must be added. And then failure to flush and add inhibitor to the system will invalidate the appliance warranty. So a boiler's warranty in Europe is no longer valid if you do not flush and inhibit the system. It makes a big, big difference. In this particular case, this is straight out of a Baxi Luna UK version of their boilers. But that's standard almost every single boiler manufacturer in Europe. So water treatment is really critical. I mean, we really want to protect the water, hot water systems. We want to clean it, we want to protect it, and then we have to maintain it. There are three aspects to this. So for a system cleaner for all systems, we sell a product called Sentinel. It's the X800 cleaner. It cleans systems in about an hour. I think the ratio is 25 to 1 water to chemical. It dissolves corrosion debris, works in cold systems. It's excellent for power flushing. They actually make a power flusher if you want to just flush it out quickly to get the job done faster. And they also, for new systems, they make the product called X300. It cleans new systems up to 6 months old, and it basically prepares it for an X100 inhibitor. And that's the key thing. The next thing you know is you need an inhibitor. In this case, this is a rapid dose cleaner, but the inhibitor is this called the X100 product. This inhibitor, what it does is it really works very well to make sure that the corrosion, it stabilizes in there, prevents rust, prevents magnetite. It does a lot of things to keep corrosion and pitting, prevents scale buildup. It does all those things. Let me take a look. Take a look at a quick video here. That's the X100 inhibitor. It's a rapid dose device. They also make it in quart and liter and gallon cans. It's a heavy duty inhibitor. It prevents against lime scale and corrosion. It's the leading water treatment product that's found in Europe. It saves energy. It eliminates dead zones. It pH neutral. And one of the things that after you put this in, it should be tested annually. And they make a test kit, which is a simple way to check that the system is treated. Take a simple sample of water, of the boiler water. You can check the inhibitor to make sure it's been dosed correct level, protection of lime scale, and corrosion. And they make simple test kits also. So really, this is the maintain part. So first you want to clean. That would be the X400 or X800 if it's an old system, X800 or X400. Inhibit, protect, and then maintain, which is the sample test kit. And, you know, today's boilers are not your father's boilers. They have much more narrow waterways that are subject to clogging. They have ECM pumps that you find, and there's low tolerances for magnetite. I'm going to show you something taken directly out of a Lochinvar installation operation manual. One of the things, the magnetite, which is basically melted iron, it's iron particles that is flowing in the water. I suppose any of you have ever done a radiant heat installation with clear tubing. You install, and very shortly thereafter, you find that there's a variety of dark black streaks inside and in the bottom of the tubing, and that's magnetite. And magnetite is pretty much in all systems, in all hydronic systems. There's too many iron components to prevent it from not leaching into the water. And Lochinvar wants a field supplied magnetic separator as a return line as close as practicable per the for the magnetic separator's instructions. They require that. And we offer a couple of these units for smaller residential applications. We use the same manufacturer, Sentinel, gives us a Vortex 500s. They come in 3/4 and 1 inch. And here you can see how they actually operate, at least in general, how these magnetic separators operate. So it's pretty amazing, as you can see, how the magnetite immediately attracts to the magnet, and then later on, and you can see there's a connection on the bottom. You can open the bottom up and flush out the residuals that are in there. There's isolation valves on the side. Another manufacturer, when we get to larger systems, say 1.5 up to 6, 8, 10, 12 inches, we have another company called Boiler Mag. This provides filtration also in much larger sizes. Same principle, has a magnet in there. It's really essential in modern systems that we eliminate magnetite, as it really corrodes and can destroy a variety of components, and especially the boiler and ECM pumps. So that's going through all the components. Now let's consider the next subject, which is going to be piping concepts. So, you know, this is the traditional way, or what we used to do when connecting a boiler up. You had a compression tank on the top, and flow check valves, relief valve, boiler pump was pumping into the boiler, or pumping out of the boiler, and then you had an air trough fitting. I mean, this is what we used to do. And this is what we should be doing now. As you can take a look, notice what we have here is air elimination device. We have our expansion tank here, and we are now, all the pumps are pumping away from this expansion tank. Here you can see we have 3 zones going out, and also connection for the indirect water heater. So let's consider ways that you can pipe your radiation and connecting your boiler to the system. First one is one pipe series loop. That's what's it's what was used most of the time for years. It uses less pipe, it's less expensive, can't zone without a bypass, has a large delta T, and radiators at the lower end will get a lower water temperature. I mean, if we have 180 coming in here, we drop some heat here, so we go to 165 here, or 178. Then over here we have 170. Then over here we have the next larger radiator. We get down to 160. We end up having like 160 going in here and having 150 coming back. The temperature throughout there will not be consistent. A better method is to have a Monofloatie system. Now in that case, the water flows through there. It branches up to the radiator and out, and then what that does is it creates an equal change in temperature across all the radiators. So the amount of the temperature of the water going in there is pretty stable. The water temperature stays constant. It's easier to zone, allows you to make connections to provide heat for specific rooms and control those temperatures within the specific rooms. How do they work? It's a Venturi T. Very simply, the main water comes in this way, it creates a pressure drop. The water comes back from the radiator as such. That pressure drop allows the water, as you can see in this diagram here, diverts some of the water through the radiator, and the rest of the water goes straight through. This pressure restriction in here allows some of the water to route up through the radiator. It basically splits the flow. It uses more pipe. It's more expensive. But the advantages are it's easy to zone. Okay, we're talking about a 2-pipe direct return system. This will use more pipe. It's easy to zone. The delta T will vary, and radiators will not get equal flow. Okay, some of the radiators, if you consider the flow, the water isn't always going to go to the path of least resistance. So if this is further away, you're gonna have more flow through some radiators than other radiators, depending upon the size and the pressure drop through the radiator. The way to solve that problem, to get equal flow through the radiators, is to do a 2-pipe reverse return system. It uses more pipe. It's a little more expensive. It is easy to zone. It will balance out the delta T, and very importantly, the radiators will all get equal flow. The secret to a 2-pipe reverse return system, as you can see, this is the first one in, and it's the last one back. It's very simple. First one in, last one back. Last one in, first one back. That's how you do a 2-pipe reverse return system. So take a look at our typical near boiler piping. And here's for a combi boiler. And as you can see here we used a primary secondary header. You have your expansion tank, your system pump, you have zone valves going out. You got a primary secondary header. Here's your feed valve. You'd have a backflow preventer here. And that would all be on the heating side. On the domestic hot water side, you would have a domestic hot water mixing valve, a domestic hot water expansion tank. And if you find this, I mean, people who install this are pretty comfortable with it. I'm sure a lot of you guys are professionals, but if you find this pretty lengthy and not the most efficient way to do it, well, we now offer a new product called the Hydro Header, and the Hydro Header does all that piping for you. Here you can see the unit the way it comes, and then you can see it actually hooked up in a real application. It takes care of it with 3 zones, and it's all ready and rocking, ready to go. So let's take a look at some other piping concepts. One of the things is that we highly recommend is primary secondary piping. As you can see here, the expansion tank is connected to the bottom at this point, so that now all the system pumps are pumping away from this, and all the other pumps are pumping away from the expansion tank. You have the system expansion tank here. We've taken these indirect water heaters, and they're connected as a zone, and then all the other zones go out. This is an actual drawing that we did for an actual installation. All of these drawings that you're going to see are like that. Again, primary, secondary piping, and then you can see how we pump away from the expansion tank each and every time. Same situation here, similar situation, effectively the same orientation here. Again, same thing, except here we have just, multiple zones. Same thing. We're always pumping away from the primary secondary headers, which is hooked up to the expansion tank. Here we see larger pumps here with the large scale, end suction pumps here, and again, same situation. Once again, you can see now this is interesting. Instead of using a primary secondary header, we used a buffer tank. Why would you do this? Why not use a primary secondary header? Well, if you look, you could have some very small zones over here. If you see this comes out and it goes to a bunch of zone valves over here, we could have really small zones in this radiant loop so that you could have calls for heat for very small spaces. Typically, if you have a vestibule and entrance, and you have a lot of kids coming out or coming into the kitchen where you have a lot of people, a lot of traffic, that space could constantly call for heat, and it requires very little heat to heat that space up. And what that could do is that could short cycle the boiler. And as a solution to that, we offer a buffer tank in lieu of a primary secondary header. They come in a variety of sizes. They can be pretty large or they can be small. The smallest one I think we make is 30 gallons. They're made by Lochinvar. You can connect them directly, use them in lieu of the primary secondary header, and it's a really good way of getting rid of applications where you run the risks of having zones that are very small, especially in radiant heat, that can be constantly calling for heat and short cycling the boiler. Here we see a larger building with a custom primary secondary header, and we go into a 4-way mixing valve for temperature control and connected to a series of pumps, once again also pumping away from this from the expansion tank. Here we have another primary secondary header connected with a simple installation. Again, the expansion tank is connected to the bottom, and we pump away. Notice that we pump away on the return side from the expansion tank. And also here we have a 3-way mixing valve going to zone valves, very simple, and also going to direct, say, to a larger zone, maybe an air handler or something along those lines. Here you can see a prefabricated header. That was fabricated by Aquatherm, which is a polypropylene piping, and they can prefabricate it, connected to a larger boiling system and larger pump system. Here we see again another primary secondary header connected to this custom unit, custom setup before. Taking a look at near boiler piping, and you can see what we have here is we have our zone valves and control flow check valves controlling this thing to get rid of any ghost flow connected into this primary secondary header. We got 2 boilers, 1 output, 1 zone coming out and then feeding out to other zones. Here you can see again another application. This is showing again what we have here. You got your flow checks, your isolation valves on both sides of the pump coming in and then connecting and tied into the primary secondary header. Same type of situation, this time with 3 boilers feeding 1. And here you can see we have 4 boilers feeding a large system, 3 pumps. One of the things is we talk about zoning a lot, and you can have thermostats and electronic controls, but sometimes you just have a simple zone over there, and the thermostatic radiator valves can provide a lot of benefit. They're non-electric, they're self-contained, they're self-radiating, they give great zoning capabilities, simple to operate. These products, you set the desired temperature, They modulate the flow into the radiator based on the ambient temperature, the ambient air temperature. They really save so much money that most Con Ed and LIPA, for the most part, will give a rebate on these units whenever you're installing these units, because that's how much energy they save. Thermostatic valve assemblies save energy when ambient temperature rises. You have solar gain, they slow down the flow, they keep the radiators cool. So they're always good to be used. Here you can see an application using a TRV, where you have a zone with monofloaties feeding here you got your boiler and you're feeding it, and you can see the TRV is here, and also TRV going into the baseboard over here using monofloaties. So again, it's a great way of zoning, and something that you can consider when putting a heating system together. They have really good advantages, and they make them also for one-pipe steam applications as well as modern hydronic systems. Here you can see another application, and they're ubiquitous in Europe. I at one time gave some training classes on there. I was with the Danfoss representative. They made 15 million of these in 1 year. That's how ubiquitous of them they are in Europe. They're really everywhere. Okay. And here you can see, here we talk about zoning with parallel direct return. We're talking about zoning options now. So one was we use these thermostatic radiator valves. Another option would be to have zone valves connected to the emitters. You want to put a differential bypass because you don't want to be deadheading the pump unless you use an ECM pump, in which case it's not really necessary. And this is a perfect application where you would want to use an ECM pump with proportional pressure control. So as you can see here, we have various heat emitters with zone valves connected to thermostats. And this is one application. Like I said, really in an application like this, if you have a conventional pump, you do need a pressure differential bypass valve. I would highly recommend in an application like this to use an ECM pump, especially something like the 2018, which you could then just set for proportional pressure control. It would automatically adjust to as the calls for heat for these various emitters come in. Here's the same thing done with a reverse return application, where again it makes the first one out in the previous one. Again, first one in was first one back. Here, first one in is the last one back. Another important point is on this too, in both applications, as you can see, the pipe size starts to reduce as you get further down the path. So you can reduce your pipe sizes as less water is flowing. You're going to consider some of the water is going to already go this way, and as less and less water is needed, pipe size can be reduced further down the line. Another option, which I find done many applications, especially in radiant heating applications, is to zone by circulator. Usually they use a control valve control box where they wire the thermostats to, and they turn the pumps on and off for each zone. You can have various. They can either be a high temp or a secondary temperature. One of the advantages of Lochinvar boilers is that when you have multiple temperatures like that, each one of those you can set a different reset curve for those different water temperatures. Here you can see, so in this case, where you have a low temperature, like a radiant heating zone, we have a mixing valve with a much lower temperature. You could also put a sensor here and then adjust also for this curve as well, for this temperature as well. And here we have zoning with zone valves. Once again, you can see you have a backflow preventer feeding a air separator, your expansion tank, you're pumping away from the system. Zone valves are going up. You should have a differential bypass, or again, if you have an ECM pump, it's not necessary. Here you can see zoning with pumps, same situation. Don't need a differential bypass because the only time this flow is going to be there is when the pumps are on. Let's talk a little bit about electronic controls. This is Lochinvar Smart System. What you see here is various situations. The red indicates that a lockout of failure. The yellow indicates that service is needed. Maintenance, notice this, maintenance required, Jones Plumbing and Heating. You got a phone number there. This will come up. You set this up by either the number of hours or the elapsed time, perhaps once a year. So if you set this up today, which is what is today? The 16th, the 17th. So if you did an install February 17th, 2021, then February 17th, 2022, the screen will turn yellow. And then when it's really operating properly, it's a blue or bluish green, which says all systems are go. Taking a look, you can either get this screen as one screen, which shows that in this case the system pump is on, the domestic hot water tank pump is on, so there's a domestic hot water priority. It's operating at 55% fire. Zone 2 is calling for heat. Hot water, it's in domestic hot water tank is on. The system temperature is set for 130. The tank temperature is set for 130, but it's actually at 124. That's why you have a call for heat. The outdoor temperature is 39 degrees. Inlet temperature going into the boiler is 148. The outlet is 165. And there's domestic hot water recirc temp is set at 127. And then if you can take a look, similar situation, you can actually see the system itself. And they actually show it to you as a graphic so you can see exactly what temperatures are operating and where. These systems, so there's a lot of benefits to the smart system. It comes with outdoor reset and has an outdoor, comes stock, all their boilers come stock with an outdoor air sensor. As an option, you can get a wireless outdoor air sensor. It has domestic hot water prioritization. You can control up to 4 pumps. The boiler pump, you can control, it has a connection for a boiler pump, a system pump, and the domestic hot water pump for an indirect, and then also for a recirc pump. Comes with automatic freeze protection. The temperature drops, it'll automatically go into low fire to maintain a sufficient temperature. Has runtime and alarm contacts. Once again, like you saw before with that yellow screen over there, letting you know that's either that it's been running for too long and it needs service. There are 2 terminal strips on it, one for high voltage, one for low voltage. Comes with a clock. Data logger. What's really important, it tells you, it always gives you your any previous failures or lockouts can be monitored on the data logger. But what's really, really cool about it is that it gives you those or do not come up as error codes. They're in plain English. If it's a flame failure because the burner went out, there was no flame, it says flame failure, not E27. There's a maintenance reminder. If there's low water flow safety control and indication typically built in, and password security. The other thing is that multiple boilers work with can be cascaded together. And what's really cool now is with new units, if you connect an outdoor sensor, a system sensor, and the heat demand sensor, and you wire it to each one of these boilers, even though you set boiler 1 as the master, if that fails, boiler 2 will automatically take over. It becomes there's redundancy in the cascading, so that if boiler 1 fails, there's nothing that needs to be done by the operator. It will automatically shift over. As part of the cascading system, you can connect up to, I believe, 8 boilers to this, and they all talk to each other. One at various times that it'll alternate operations. So typically in 24 hours, boiler 1 becomes the master boiler today. Tomorrow it's boiler 2. The next day it's boiler 3, etc., etc. The coolest thing is that a lot of the new products, especially the new Night, the Crests, and especially with the new KB, the Night XLs, they come with standard as Connexus. And Connexus is It is a cloud service. You can connect your boiler. You can access your boiler from anywhere where you have an internet capability. As long as there's a Wi-Fi signal that can be picked up, an internet Wi-Fi signal by the boiler, you can then control your boiler using Connexus. It's free with the purchase of a control. The cloud service is free with the purchase of a control. It allows you to troubleshoot or look at a boiler. If your customer connects you with, if your customer connects you with, if you get a call and he contacts you, and you decide that you can actually go online, look, and find out what the failure is. So before you make a service call, you can have a rough idea what needs to be done. Also, you can also maybe readjust or connect or fix, make adjustments to the controls to the boiler at a remote location. Additionally, if there's failures or if failures, it can notify. I believe via email, it'll send an email out if there's a failure. So it gives you really total remote access. It's like I said, it's so beneficial. It's come stock in a lot of the new units, the Crests and also the new Night XLs. Here you can see the types of control, what the unit is modulating at, all the system temperatures, the demand, what the demand is. You can see that it provides everything that you can get on the screen and you can get from the system, you can get from Connexus at a remote location. So as we start to wind down, we have some really take-home messages. So key things that we want to really focus on here. And the first most important thing is that the net BTU divided by 10,000 gives you the flow rate. So once again, if I have a 250,000 BTU boiler divided by 10,000 means I'm going to have a flow rate of 25 GPM. If I have a 105,000 BTU boiler, then I'm going to need 10.5 GPM flow rate. That's how I determine the flow rate for the boiler, and also by the heating load. If I have an air coil which produces a heating coil which produces 40,000 BTUs, then I know I'm going to need a flow rate of 40 divided by 10,000, which is 4 GPM. So that is a really key point. If you get anything, you want to bring that home. The next thing is the maximum flow rate that you can get through pipe size. Again, half inch is 1.5 GPM. 4 gallons a minute through 3/4, 8 gallons a minute through 1 inch, and 14 gallons a minute for 1 1/4 inches. Pump head. How do we calculate the pump head? Measure the longest run in feet, add 50% of that number, and multiply that number by 0.04, and that gives you the flow head. That gives you the pump head. That's the quickest and easiest way to calculate how much head you need in your pumps. The maximum flow rate and heat carrying capacity. So the most, at a 20-degree delta T, the most heat that you can get through a half-inch pipe is 15,000 BTUs. 40,000 BTUs through 3/4 inch pipe. That's a pretty, when it comes, if you're doing residential work, that's a really important number to remember. 3/4 inch pipe, 40,000 BTUs. If I have more than 40,000 BTUs, I need to set another branch or another zone out. 1 inch pipe, 80,000 BTUs, and 1 1/4 inches is 140,000. Okay, baseboard size element. Typical BTU per linear feet at 100. This is at 180 degrees water temperature and a 20-degree delta T. Remember that if we use a modulating boiler in a modern system and we drop that water temperature, the amount of BTUs is going to drop accordingly. So the big number there is on a 3/4 inch baseboard. It's going to put out about 600 feet per linear foot, which is about 67 feet maximum baseboard loop. Half inch is going to be about 25 feet maximum baseboard loop. 1 inch at 104 feet, and 1 1/4 inches at about 177 feet. The total number of convectors a pipe can serve. So if I have a 5100 BTU convector, half-inch pipe will serve 3. 3/4 inch pipe will serve 8. 1 inch pipe will serve 16. Sharing pipe size, okay? So if I have 1/2-inch copper with a maximum flow rate of 1.5 inches, and then 2-inch copper at 45 GPM, 2-inch, 1/4-inch steel, here you can see the various maximum flow rates for the various pipe sizes. This is useful information, especially when you get the larger systems. Or alternatively, I strongly recommend you can download Bell & Gossett System Sizer, which you can get either from, you can either go to bellandgossett.com and you go to I believe it's just type in System Sizer, SYZER, or you can get it, just Google through the iPhone store or Android store. You can also download it for your iPhone. That's how I usually use it. I have an iPhone. I use it directly on my iPhone all the time. Now, looking at a size expansion tank, I'd say the easiest expansion sizing program that we have is tank sizing program. Very useful. Is one of our companies, Xylem. I would strongly recommend you try this out at xylemusa.com. It's an excellent resource. It's a nice, smooth, easy to use program. Works well. And then I think something I would highly recommend you connect to is Lochinvar U. This is the home screen for Lochinvar University. You can reach it at lochinvaru.com, and it has all kinds of information. I mean, if you look back, there's all kinds of tutorials and instructions. Very, very useful website. And then, of course, Bell & Gossett's Learning Hub. You can go to Bell & Gossett, you can go to Training and Education, and from there it can take you right to their training hub. Highly recommend you go in there. Bell & Gossett, the website is bellandgossettmarketing.com/schoolhouse, or you can just go to Bell & Gossett's regular website and go into training and take you right there. And for you contractors, I cannot strongly recommend you consider joining Lochinvar's VIP program. If you're putting in residential boilers, there's various rebates, 2020 rebates, $125 per model that you put in. Here are the various sizes, WHBs, KHBs, et cetera, also for the indirect tanks. Just go to lochinvarvip.com and get rewards and credits from Lochinvar. They would very happy to have you join. I highly recommend it. Just Wallison is ready and willing to work with you and your team and assist in system design, equipment selection, and troubleshooting for all of our product lines. We're always available. Just give us a call. And thank you. And do we have any questions?